Hello everyone, welcome back to Networks class. So last time in class, what we discussed was finishing up storing graphs in a computer. So you should all know about things like compressed sparse row format. We also talked a few definitions on graph structure. So you should know about what a path is and what a cycle is, for example. And we just began talking about the shortest path problem. So we didn't really see any ways of solving it, but we just defined the problem. And the plan for today is to look at how we can solve shortest paths using a linear program. After we get done with that, we'll see a few more definitions on graph structure, and it'll take us to discussing graph search algorithms, which are the basic building blocks to getting much, much faster algorithms for solving problems like the shortest path problem than what you can do using a linear program. So let's just jump into the material for today. So here is kind of the basic shortest path problem that we introduced last time. So we were given a graph with some edge lengths, and we're going to say that Cij is the length of edge ij. And we're given two special nodes, node S and node T. And our goal was to find the shortest path from node S to node T. And what that really meant was the minimum distance path. And we discussed last time how to really solve this problem, we have to assume that the graph has no cycles of negative total length, because that makes the problem somewhat undefined. So let's discuss on how we might go about solving the shortest path problem using linear programming. Now, the key to defining a linear program is defining our variables and constraints. And so to help us do that, we're going to follow the following basic idea, which is that we'll force a truck to leave S and go to T, and we'll charge the truck Cij for moving across edge ij. So that's the basic idea of our linear program. So let's use this idea to try to define our variables and constraints. So the variables that we'll use are just yij variables, and we'll say for now they're binary. So they're 0, 1. And what these variables will mean is that did the truck use edge ij? Or another way to think about these variables that's going to become maybe an easier way to think about them later in the class is just that these variables could mean the number of trucks using edge ij. So the number of trucks using edge ij is either 0 or 1. So given the definitions of these variables, and given that Cij is the length of edge ij, imagine that somebody comes along and specifies a path from S to T. So on the path, the y variables are 1, and off the path, the y variables are 0. So we can write down the cost of the whole path in the following way. So the cost of the path is just the sum over all edges ij of the Cij variable times, or the Cij piece of data times the Yij variable. So in the sum, we're exactly charging for the edges that the truck is using, and we're not charging for the edges that the truck is not using. And so this sum is going to be the objective function of our linear program. So we're going to want to minimize this over the Yij variables. But as written so far, somebody could come along and just say, okay, so I have to minimize this sum. the y variables are either 0 or 1, so let's just set them all to 0, and that'll make the sum be equal to 0. So right now we're not forcing the truck to leave S and go to T. So let's write down some constraints using the y variables that are going to do that. So the first thing that we need to do is we need to force the truck to leave S. So let's think about how this looks. So here's our node S, and it has some edges going into it, and it has some edges going out of it. And what we want to say is that the truck has to leave S. So let's do it like this. Let me first write down the constraint, and then we can talk about what it means. So what we're going to do is we're going to sum over all of the edges that come into S. Then we're going to subtract all of the edges that go out of S. And we're going to say that that is equal to -1. So what this is saying is that one more truck has to leave S, then enters S. So one more truck leaves, then enters. So this is basically the thing that's forcing the truck to leave node S. So the other thing that we wanted to do was force the truck to stop at T. And we're going to do this in a very similar way. So we can just sum up everything that goes into T, subtract out everything that goes out of T. And if we want the truck to stop at T, that means one more thing has to be coming into T than is leaving T, so that's why this is going to be equal to 1. So this is basically forcing this truck to stop at T. But we're not yet done, because we also need to say something like that at every other node besides S and T, the truck can neither start nor stop there. So every other node is kind of a transshipment node, where if the truck enters that node, it has to leave. So for every other node, if the truck enters, it has to leave. And the way that we can write down those constraints is as follows. So we're just going to sum up over everything that enters the node. We're going to subtract out everything that exits the node. And those two things have to be equal. So we're going to set that equal to 0. So right now, we're forcing the truck to leave S. We're forcing the truck to stop at T. And we're making sure that it can neither start nor stop in every other node. So this is for all nodes A, such that A is not equal to S and A is not equal to T. And so these constraints, along with our objective function and the binary restrictions on the y variables, are enough to solve the shortest path problem. So let's write down the entire shortest path LP that we came up with. So it was minimize over these yij variables, the sum of the cij times yij, and the sum is over all edges, such that the following is true. So we have everything that goes into S. We're subtracting from that everything that goes out of S. So the truck has to leave S, so that's equal to a -1. It has to stop at T. So we have everything that goes into T minus everything that leaves T. So when we set that equal to 1, we're saying the truck has to stop at T. For all other nodes, the truck can neither start nor stop there. So that's going to be equal to 0. And then we have that these y variables have to be 0 or 1. And of course, all of these sums here are over the edges, or over edges that look like look in that particular form. So this sum right here would be over all edges that start with t and end in some other node I. And this last constraint is, of course, for all nodes A, such that A is not equal to S and A is not equal to T. So this is the program that we came up with, and you know, it's perfectly fine if you go and if you type it into a solver, or if you type it into a modeling language like GAMS, and you hit solve, it will find the shortest path for you. But right now, if I just stop the story here, you should be a little bit upset. And the thing that should be upsetting you is that this program is very, very inefficient. And the thing that makes it inefficient is exactly these binary constraints. Because if we went off and we used Cplex to try to solve this, then what would happen is we would be using some kind of branch and bound to try to figure out what the y variables are. And you should all know that that's just very inefficient. I mean, branch and bound is essentially almost brute force. So you should be very unhappy about these binary constraints. But it turns out, and this is some magic that we're going to get to very soon, that you can drop these binary constraints and you can just substitute them with the yij's bigger than 0. And it just magically turns out that for this particular LP, because of the structure of its constraint matrix, when we drop these binary constraints in favor of just this simple, the yij's being positive, when we go off and solve the problem, we're going to get answers that are exactly binary as we wanted them. That all the y's are going to be either zeros or ones. And we'll talk in just a few lectures why that is. For right now, it's a bit of magic, but this is how we can finally get to a linear program that's for shortest path that's efficient to solve. So you can go off and use simplex method or any of your other regular linear programming methods to try to solve this program. So let's discuss how quick we can solve a program like this. So we do have the program. We can program it in GAMS, like it'll give us an answer. But what's the running time of solving shortest path? So solving shortest path using an LP solver. So the fastest algorithms for LPs that we know of run in time O of big times small squared. And what I mean here is that big is the bigger of the number of variables and the number of constraints in the problem. And small, of course, is the smaller of the two. So let's just use this running time, big times small squared, to see how quickly we can solve shortest path as a LP. So for shortest path, what are the number of variables? So how many variables does this program up here have? Well, the variables are, of course, the yij's. And we're going to have one yij for each edge. So the number of variables is equal to m, because that's the number of edges. And we have one y variable for each edge. What about the number of constraints? So we basically have one constraint for every node. So this is a constraint for S. This is a constraint for T. And the third one actually has one constraint for every other node besides S and T. So in total, we have n constraints, one for each node. And of course, these constraints are telling things like we're forcing the truck to leave S, we're forcing it to stop at T, and it can neither start or stop on any other node. These non-negativity constraints at the end here, well, we won't count them as constraints because they're just simple non-negativity ones. So our shortest path program here has m equal to the number of variables equal to m and the number of constraints equal to n. So typically we're going to assume more edges than nodes in our graph. So we're going to assume that m is bigger than n. And so that gives us a running time. So the bigger of the number of variables and number of constraints is m. So our running time is going to be m times n squared. So that's the bigger times the smaller squared. Now, this turns out to be actually very slow, just excruciatingly slow. And let's just do a very quick example of this. So if I have a graph with 1,000 nodes, how many edges can this graph have? Well, the number of edges, m, is always less than or equal to n squared in a graph, let's say not a multigraph. So I can have one edge for each pair of vertices, and that's why m has to be less than or equal to n squared. So the number of edges in this graph with 1,000 nodes can be up to 1,000,000. So we can have up to 1,000,000 edges, but let's say that we have just a modest number. So let's say that we just have 3,000 edges in our example here. So a graph with 1,000 nodes, 3,000 edges. Let's figure out what the running time here is. So it would be 3,000 edges times 1,000 nodes squared. So this 1,000 squared right here is giving us 1,000,000 operations. So we're getting 3,000 million operations, which is like 3 billion operations to solve shortest path on this reasonably small-sized graph. So, and in practice, of course, you know, if you run simplex method, it happens to run a little bit faster than this. But nevertheless, it's just very, very slow. And this is the basic reason why there exists a networks course in the first place, is because networks problems are special. They're special because we can solve them much, much faster than these general purpose linear programming algorithms that we apply to other linear programs. So very soon in class, we're going to see algorithms for shortest path that work just blazingly fast compared to this general purpose linear programming solver. If we compare to using a general purpose linear programming solver for solving shortest paths. So that's the basic idea. At least right now you have one way of solving the shortest path problem if you needed to. You can go off and program that linear program into GAMS and it'll give you an answer. So before we can learn these much faster algorithms for shortest paths, we have to create some building blocks. And our basic building blocks is going to be the graph search algorithms that we'll talk about next. But before we can get to those, we just need a handful of other definitions about graph structure. So here are the last few definitions that we need. So we say a node B is reachable from node A if there exists a path from A to B. So that's a pretty straightforward definition. And let's just look at our examples for this to be able to illustrate this definition. So here's an example that we had seen before. Here's another example that we have seen before. And let me just introduce a third example. So, okay, so let's use these examples to illustrate reachability. So in example 1, 2 is reachable from 3. So how would I check this? Well, I'd have to find a path from 3 to 2, and here's a path from 3 to 2. I could go from 3 to 4 to 0 to 1 and to 2. So yes, 2 is reachable from 3. Let's take a look at let's take a look at graph 3 here. So here 1 is reachable from 0, but 0 is not reachable from 1. So to reach 1 from 0, I could just take the edge. But if we start at 1, there's no way that we can get to 0. So that's why 0 is not reachable from 1. So, when people created these definitions, they very purposefully used kind of understandable English words. So that's why the word reachable, we almost don't have to write down this definition. It almost just is self-evident what it means. So let's look at our next definition. So a graph is strongly connected if for all pairs of nodes A and B, both of the following are true. So both A is reachable from B, and B is reachable from A. And so the reason I put the word strongly in parentheses here is because oftentimes people will just say connected, and what they really mean is strongly connected. So similarly, we say that a graph is weakly connected. If for all pairs of nodes AB, at least one of the following is true, that either A is reachable from B, or B is reachable from A. And finally, we say that a graph that is neither strongly or weakly connected is disconnected. So a graph is disconnected otherwise. So let's just see some examples of this. So let's take a look at this graph number 1 that we have here. So this graph is strongly connected because we can reach, for every pair of nodes, we can reach both A can reach B and B can reach A. So let's take a look at this pair 3, 4 to make sure that's true. So 4 is reachable from 3 because we can just take that one edge. But also 3 is reachable from 4 because we could just go 4, 0 and then 0, 3. And that takes us to 3. And so this is true for every pair of nodes here. So 1 is strongly connected. So similarly, 2 is strongly connected. And that's because, again, every pair of nodes, you can reach both A from B and B from A. So let's take a look at 3 and 1. So here's a path from 3 to 1, 3, 0, 1, and a path from 1 to 3, it would be something like 1, 0, 3. So what about example 3? This one is weakly connected. And that's because, so there's only one pair of nodes here, 0, 1. So 0 can reach 1, but 1 cannot reach 0. So that graph is weakly connected. And just to have an example of a disconnected graph, consider the following graph. So this is a graph. The whole thing is a graph, but it's disconnected because, for example, this pair of nodes, neither can reach the other one. So this one is disconnected. So let's look at our next definition here. So we say a graph is a tree if, when we turn its edges into undirected edges, the following two things are true. So first, it is connected. And the second thing is that it has no cycles. So let's just see some examples of this. So here's an example of a tree, and this is probably the most common thing that you'll see drawn for a tree. So this graph is connected, and it has no cycles. But here's another example of a tree. So this example is also a tree because it's connected once we turn its edges into undirected. And once we turn its edges into undirected, it has no cycles. So both of these are examples of trees. But by the way, if you look at this second graph right here, before we turn its edges into undirected edges, this graph is actually disconnected. Because if you take a look at this vertex right here and this vertex right there, neither of these vertices can reach the other one. And so this graph is disconnected before we turn its edges into undirected edges. So those are some examples of trees. Let's look at some examples of non-trees. So here's our first example of not a tree, and that's because this graph is disconnected. Here's another example of not a tree, and that's because this graph has a cycle in it. And here's another example of not a tree. And that's because once we turn the edges into undirected edges, this graph has a cycle in it. So not trees. So our next definition, and this is just the last couple of definitions here, is that in a rooted tree, we pick one node and call it the root. And we make the other nodes sort of hang from the root in levels. So let's just do a brief example of this. So here's a tree, 0, 1, 2, 3, 4, 5, 6. So this is a graph that is connected and has no cycles. And we could root it at whatever vertex we want, but here's the tree rooted at node 2. So we make node 2 be the root, and then everything else is going to hang from 2n levels. So the things on the first level are all the nodes that are directly connected to 2. So that would be 1, 3, and 4. And then from 1, 0 is going to hang. Nothing hangs from 3. And from 4, 5, and 6 hang down from there. So this is the root, and the root we say is at level 0. We say that the next is level 1. And the last one here for this example would be level 2. And we say that the depth of the tree, so the depth of this tree is equal to the number of the highest level. So the depth of this tree is 2. And we didn't have to root the tree at 2. We could have rooted it at a different node. So for example, if we rooted it at 6, this tree would have an entirely different depth. So depth is a property that's dependent on which node we chose to root the tree on. So just our last definition here. So in a rooted tree, for a node A, we say that the parent of A is the node adjacent to A on the level above. And we say that the children of A are the nodes adjacent to A on the level below. And of course, the root has no parent because there isn't any levels above the root. So let's just apply these definitions to our example up here. So for example, the parent of node 4 would be equal to 2. And we did that by just looking at node 4 and looking at which node is adjacent to it above. So that's 2. And the children of node 4 would be the 2 nodes that are adjacent to 4 below. So that would be 5 and 6. And so the last thing we need here is that a leaf node in a rooted tree is a node with no children. So the leaves of this tree that we have up here as an example would be 0, 3, 5, and 6. And that's because those are all of the nodes in that tree that have no children. And so we're going to use those terms to refer to various structures that come out of our algorithms as we run them. But let's take a look at the next graph problem that we're going to look at in detail, which is just graph search. So let's just begin by describing this problem simply. So suppose that we are dropped onto a special node in a graph that we'll call the source. So we're just going to start in some particular node in the graph that we'll call the source. And let's suppose also that we heard rumors that there is some treasure somewhere on the graph. So these are only rumors. We're not quite sure. But our goal is this. Our goal is find the treasure if it exists. And otherwise, we want to explore the whole graph to convince ourselves that there is no treasure. So otherwise, explore everything to make sure there is no treasure. And so, in some sense, if somebody just gave you a list of the graph's nodes, it should be very easy to solve this problem because you could just go through every node and look in the node to see if the treasure is in there. And when you're done looking at all the nodes, you'll either have found the treasure or you'll know that there is no treasure. But the problem here with graph search is that we only have local information. So this is what I mean by this, is that the graph could look like this. So maybe this is the source, and maybe the graph looks something like this, or maybe the graph looks like this. This is the source, and there's some nodes that are going out of that. But to us, when we start, these two situations look exactly the same. So both of these situations look like this. We know we're at the source, and there's a couple of nodes here that we haven't explored. And so we don't know the entire graph structure. We only know in the current node what are the edges that are going out of it. That's about it. And we just need to use this local information to explore the whole graph. And so search algorithms are going to let us do that. So the first search algorithm that we're going to learn about is called breadth first search. But before we describe the algorithm, let's just talk about a few key pieces of data that we need to keep track of. So the first thing that we need to keep track of is somehow whether we visited a particular node before. So we need to keep track of whether we have seen a node before. And to do this, we're going to basically keep some node colors. So the idea here is the following, that we're going to color a node white if we have never seen this node before. We'll color a node gray if we have seen the node, but we're not finished with it yet. So it's gray if basically we have some work left to do in that particular node. And finally, we'll color a node black if we have seen the node, we've explored it, and we are done with it. So these three colors are basically going to help us keep track if we've visited a particular node before. But another thing that we need to keep track of is that for each node, we'll keep track of the nodes, what we'll call search parent. And the search parent is going to be the node that led us here. So in other words, if I see node B, if I see node B from node A for the first time, then A is going to be B's search parent. So these are the two basic things that we'll keep track of, is just these colors and the search parent. So let's see, let's just write down the pseudocode for breadth first search. So oftentimes breadth first search is abbreviated just BFS. And BFS just takes in a graph and the starting vertex S. So S is the node in which we get dropped on to start our graph search. So the pseudocode for this algorithm looks like this. So we'll let Q be an empty Q. And what I mean here by the word Q is that this is just a first in, first out data structure. So you can think of this as a pipe, and we're putting things into one end, and things are going out of the other end. So the first thing that goes in is going to be the first thing that goes out. And also, to get the algorithm started, we're going to initialize all nodes to white. So this means that at the beginning, we haven't seen anything, and so all of the nodes are equal to white, except the only node that we've seen is just this first node that we got dropped on. So we're going to set the color of this first node that we got dropped on to gray, meaning that we're not done with it. That's the one that we're going to start with. We're going to set the search parent of this node to none, meaning that we just got dropped on this node, and so we didn't get to this node from somewhere else, and that's why it has no search parent. And then we're going to push this node into this queue. And that's going to start the algorithm's loop. So the algorithm's loop is the following. So while Q is not empty, we're going to do the following. So let's let U be equal to the front of whatever is in the queue. So what I mean by Q.head is that we're just going to look at the very first element on the queue. So this is the thing that we would have removed, but we're not going to remove it. We're just going to look at what's in the front. So if this node U has a white successor, let's call that white successor V. So if this node U has some white successor, it means that we've never seen this node V, the white successor, before. And so we're seeing it for the first time. And since we're seeing it for the first time, we're going to set the color of V to gray. We're going to set the search parent of V to U. And that's because node U led us to this node V. So that's why V's search parent is going to be equal to U. And then we're going to push V onto the queue so that we can process it later at some point. So otherwise, this node U, we've looked at all of its successors. It no longer has any white successors, meaning that we've kind of extracted all of the information out of node U that we possibly could. And so at that point, we're going to set the color of U to black, which means that we've kind of extracted everything out of U. We're pretty much done with it. And at that point, we're just going to pop. So this q.pop, what it does is it removes u from q. And that's because qpop just removes the front of the q, and that's exactly where u was. It was right here at the front. And so this is the very first graph search algorithm that we'll take a look at. So next time in class, we'll take a look at an example of running breadth first search on a graph, and we'll talk about breadth first search's properties. But let's conclude class here for today, and we'll pick up from here next time. Thanks a lot for listening.